Okay, so Chapter 17, we are talking about index numbers, and general idea is that you want to be able to compare two numbers in terms of a relative change, whatever that change may be, and it could be price, quantity, or value. And then we also want to look at how that is used to kind of interpret data, whether that data has to do with price, quantity, value, or some other items. We will look at some examples. So in this case, we're talking about population, and we have British Columbia in 2013 having 4.4 million people approximately, and Ontario having over 13 million. And so all we're saying is if we compare the population of the two provinces, we would say, for example, that British Columbia's population in terms of Ontario's is 34%. So the population of British Columbia is only 34% of the total population of Ontario. And really, it's just, if you look at these two numbers, this numerator and denominator, as, A over B, for example, you can just say what percent or what percent of B is A, right? What percent of 13 million is 4 million? And the answer would be 34%. Okay, so if you say what percent of B is A for any of these, it's a pretty good start, because then you'll be able to get closer to understanding that 34% of 13 million is 4.49 million. Okay, the following chart shows passengers for the 10 busiest airports in the U.S. in 2011. And we have passenger list, Atlanta being number 1, and then Houston being number 10. And if we say, well, what are all of these airport sizes in terms of passengers relative to one airport, let's call it Houston's, then we could just put Houston as our denominator, and that's where the 40.1 comes from. Here's 40.1 right there. And if we say, well, what's Atlanta's relative to Houston's, we would take Atlanta's number, 92.3, divided by Houston's number, and we get 230.2. And if we interpret that as the Atlanta airport is 2.302 times as busy, we can say that's substantially larger, right? It's more than 2 times the size in terms of busyness than Houston's. Atlanta's is more than 2 times the size. Okay, that's substantial. And then if we look at, say, San Francisco of 40.8 over the 40.1, we would say that San Fran is only 1.017 times as busy. So, of course, 1 is the same. If this was 1.000, it would be exactly the same, because the numerator would then be equal to the denominator. So anytime you have a number greater than 1, then that numerator, by definition, must be greater than the denominator. Okay, so that's why we can say 1.017. Not that much bigger, but it is bigger than Houston's.
Okay.
Okay. All right, BLS 2005, hourly earnings of production workers, 1402. That's 2005 right there, 1402. 2014, 1864. So we can say hourly earnings, right, in the later year of 2014, 1.32 times more than they were in 2005. How do we know that? Because we're using a simple index in this case to get the number of 132.81. And then if we take that 132, it's called taking it in hundredths. When you take something in hundredths, you're dividing it by 100. And that's how you get the 1.32 number. Okay, if all you did was take it one over the other, then you would get the 1.32. But technically, when you're finding a simple index, you're multiplying it times 100.
Okay.
Okay, and so
the present year divided by the past, is that what that is?
Yeah, almost always, because you want to know how things grew.
Okay.
Okay, so in that case, you're taking the present over the past if you're trying to figure out how things grow. However, if you just want to know, one number relative to another, then the denominator in that case could be anything because you want to know something relative to another. Okay, but usually it's the larger number over the smaller number.
Okay.
Okay. Okay, or I should say the later year. I shouldn't say, definitely shouldn't say larger.
I
It's
understood.
the later year over the earlier year. Okay, in many situations, we wish to combine several items. There are several ways to combine several items, and it goes into kind of differences regarding it. So, for example, if we take 1.422 over 1.042, we can do that using our Excel here. Pull this up. I'm just going to take 1.422 divided by 1.042, and I get 136, or I could say 136. What I'll do is I'll multiply this. That's what it was. Times 100. There we go. So 136.5. Okay, that's where the 136.5 comes from. So if I were to move this just to one decimal, there we go. So there's the 136.5. And if I did that for all of this data, okay, this is the simple index I would create based on the slide we just went through. And all we're saying then is divide it by the n, right? The number of observations, and there are 6 observations. So there's your 6. And our answer will be 152.2. But when we think about it, right, what are we doing first? We're understanding how much prices have increased over this 10-year period for bread, white cost per pound. So bread has gone up 36.5%.
Okay.
In this period. Eggs have gone up 64.5. Milk has gone up 31.3, etc. So we see a price increase from 2003 to 2013 for all of the goods. And then we're just saying, on average, how much have prices gone up? And so we take these price increases, okay, the simple indexes, and we divide them by the n. And so we could say in general, right, or on average, the price of the 6 items increased 52.2%.
So that 913.2 is the total of all those numbers.
Right. Exactly. Exactly. And you could probably visualize how you could do this in Excel.
Yes.
Right. Just taking, the number, each number over the other one, and multiplying it times 100, getting this column, dragging it down, getting this column, and then just find equals average, boom, and you got the 152.2. Okay. And of course, that's how you want to practice it.
Right.
Okay, and then we have a unweighted, right, or these are both unweighted, but then we have a simple aggregate index where all we're doing the same prices, right? 1.042 is the same as this 1.042, and you see the sums down here, right? And we're now going to take those two sums, right, and divide them by each other, and then multiply times 100 as you always do with the simples, and you get 156.1. Of course, that's different than 152.2 because we use a different technique, right? In this case, the averaging, I should say the summation of these led to the numerator and denominator, whereas before, all we had was the summation of the average of the simple indices first.
Okay.
Okay, so that 913 comes from the fact that we individually found the price changes and then found the average, whereas here we just added them up. Based on this way, the aggregator combining data, the price of the 6 items increased 56%. So you do see a bit of a bias towards you do see a higher outcome, when you just add things up. As long as you know how you did it, then you can make the proper interpretation.
Okay.
Okay. The Laspeyres. So note that the price of each item are weighted by the quantities consumed in the base period. Then these weights are summed over all the items in each period to calculate the weighted aggregate index. So this is still, we're still, or now we are weighting based on whether or not we're looking at a base period or a current period denominator. Okay, and as you see, price index, current price, price in the base period, quantity used in the base period. So if we're interpreting, let's look at the denominator here. The price, okay, and that price is going to be in the base period. The base period is going to be your earlier year.
Okay.
So PO is going to be the earlier year, QO is going for prices, and QO is going to be the earlier year for the quantity. Whereas PT is the current price, which is the later year, times the base quantity. Okay, so this is one technique where the primary focus here is taking your base as your earlier year as your denominator.
Okay.
Okay, so you want the base as your denominator. So whatever you get for your numerator is going to be compared to what both items were in the earlier period. So we see the earlier period, 2003, where we have price and quantity, and we see the newer period, 2013, also price and quantity. So real quick, eggs for a dozen cost $1.18 for 20, and we're talking 26 of them being sold or purchased in 2003. And then you see the price went up, right, 10 years later, and the quantity about the same, but it is different because people may have purchased, or they did purchase a different amount during that year. And of course, this is probably, be 20 million if we're looking at BLS data. But just to simplify, we can say 20.
Okay.
Okay, so look at our formula again, PT over QO, right? And PT is the price in the current period. So that'd be $1.42 times QO, which would be the quantity in the base, which would be 50. Okay, so that $1.42 over 50 is what we're talking about. So if I do that math, all right, 1.422 times 50, all right, 71.1, and that's right here. Okay, so we would take that number, right, and we would just create a column of that number, and we would add that number together, that whole column, and we would get 692.77, which is PT times Q added together.
Okay.
Right there. And then divided by PO over QO, okay? And so PO right here, 1042 times QO, 50. 1.042 times 50, there is your 52.1 right here.
Okay.
And that 52.1 plus all of the other POs times QOs gets added together, and then we get our denominator.
Okay.
Okay, and it's times 100, so we can say 140.28, which means the items increased 40%, 40.28%. Okay, which of course is different than what we saw here, because here all we had were prices. Right? All we had were prices, and we were trying to find the increase in price over this 10-year period for these 6 items. And we said, well, first time it was 52%, just based on price alone. Second time, 56%, different way to calculate with price alone. And now, and remember, those are unweighted.
Right.
But if we weight it, and what's the weight? The weight is the quantity.
Right.
When we introduce the quantity as the weights, we then have a more accurate ability to tell us the price change, because now you're factoring in how much was sold. So
Okay.
when I multiply 1042 times 50, I'm giving a certain amount of power to 1042. Right? When I multiply, for example, 299 times 12, I'm giving a certain amount of power to 299. I'm actually diminishing the power of 299 and increasing the power of 1042. and I'm really increasing the power of the milk because milk was sold the most. So the power of 2.686 is most prominent in the calculation because we weighted it by a higher weight relative to the other weights.
To the lower weight.
Yeah, exactly, exactly. So that's the power of weighting. You're giving stronger emphasis to the prices. Price is still the most important thing here because we want to know how much prices change. That's our question. But we're giving emphasis to more important prices because they sold more. So they should be more emphasized as opposed to this, which only takes each price as an equal. Right? When you add something up and divide it by the number of n, each of these are treated equally in terms of their weight. Right? Technically, you're taking 1.042 times 1/6, 1.7175 times 1/6, 2.686 times 1/6, because all of the weights must be equal, right, in order for you to, by definition, to get the average. So that's why we want to weight things almost always. I can't think of a time where not weighting is good. Okay, so that's Laspeyres. So Laspeyres gave us 40.28. If I had three of these to choose from, 52.2, 56.1, and 40.28, of course, I'm choosing 40.28 because that's giving you the better, more accurate increase because of the weights. Now, of course, other folks came up with different ways to weight. There's the Paasche, and the Paasche is saying, hey, instead of using base year price and quantity, instead of using earlier price and quantity, PO/QO, use the early price, okay, the original price in the base period, times the quantity in the current period. Okay, as your denominator, and your numerator use all new things, price and quantity.
Okay.
So the difference here, of course, is the QTs. Okay, this was QO before, and that was QO before. If you look at the Laspeyres, so you see QO, right? Paasche is saying utilize QTs in terms of your calculation. PO, just look at your numbers. PO right here times QT, which would be right here. So I would take 1.042 times 57.31. Okay. And so I add all those up. There's my denominator. And then if I take 1.422 times 55, I get the 7821. Add them all up. There's my 803 right here.
Did that lies at 1.422? You did that for the present year. You multiply that time, that 55, instead of the previous year. The first one you did the previous year multiplied by the present quantity, and now you're doing you're multiplying the price times the
newer quantity. Correct.
Okay.
That's correct. Exactly. Okay. Yep. The price 1042 times the 55.
Right.
Exactly.
Okay.
Okay. So in play here are all the new quantities. That's the big change.
Okay.
Okay. And so 38% is Pasche's claim of how prices have changed over this period, whereas Laspeyres says, no, it's 40%. But as you see, they're very close. They're very close. So Fisher says, take them both as a geometric mean. And all that means is take the square roots of the multiplication of Laspeyres and Paasche to get the ideal. And of course, ideal meaning taking the both of them together and finding the geometric mean. Now, and the importance there is, it's going to be very similar. If you actually took the average of these two numbers, 38.9 and 50 and 40.28, you would get a number very close to the geometric mean, which turned out to be 39.6. Okay, so there's your geometric mean, and that gives you a number that's in the middle, okay, of the Paasche, 38.9, and the Laspeyres, 40.28.
Okay.
Okay, so that's all the ideal index is. Value, you can, now that you understand what I've just done, you could pretty much do the value. Shouldn't have a problem there.